Hello guys, and welcome once more to this video into our YouTube channel. So in today's video we are going to be solving a question on mechanics, more specifically a question on connected particles. So in today's video we are going to be solving a Cameroon DC examination. That is, we are going to be solving the pure mathematical mechanics paper 3 question of June 2014, more specifically question 6. So this particular question was a very interesting question on connected particles, where we have two particles which are lying on inclined plane. That is, one part of the inclined plane being rough and the other part of the inclined plane being smooth. So without wasting any time, let's launch into the question proper. The question reads: two particles A and B of masses 2m and 6m rest on the smooth and rough inclined faces of a fixed wedge as shown on the diagram above. They are connected by a light inaccessible string passing over a smooth pulley fixed at the top of the wedge. The smooth face of the wedge is inclined at 30 degrees to the horizontal, while the rough face is inclined at an angle of 60 degrees to the horizontal. So that part. The system is released from rest with the string taut. Given that the coefficient of friction between B and the plane is 2/3, show that A, the acceleration of the particle is 3g divided by f times square root of 3 minus 1 meters per second squared. B, the tension in the string is mg divided by 4 times 3 square root of 3 plus 1 Newton. C, find in terms of G and M the force exerted by the string on the pulley. The particle B, that is the paragraph which introduced the next question. The particle B hits the ground 2 seconds after the system is released from rest and does not rebound from the ground. D, show that the further distance A travels before coming to momentary rest is G times 3/4 times square root of 3 minus 1 then squared meters. Let's actually launch into the solution of this question. So we have been told that we have two particles which are connected by a light inaccessible string which passes over a smooth pulley fixed at the top of the wedge, and the masses of the particle, that is the mass of particle A, is 2m and the mass of particle B is 6m. And we are also being told that the smooth face of the wedge is inclined at 30 degrees to the horizontal, while the rough edge is inclined at an angle of 60 degrees to the horizontal. So the reason why I indicated these two lines, which indicates that this part of the plane is rough actually. So having this as condition, we want to answer the A part of the question. That is, we want to show that the acceleration of the particle is 3g divided by 8 then times square root of 3 minus 1 meters per second squared. So before we launch into that, the first thing we need to do is indicate all the forces acting on this our system. So I've first of all indicated this tension here, the tension acting on our system. Obviously the tension is acting on our system, but remember, these tensions cancel. That is, the tensions which are closer to the pulley cancels actually. So when we are going to be working, we are simply going to be working with the two tensions, that is the tensions which is immediately connected with the particles. Why? Because at this level, at the pulley level, these two tensions will cancel. So after indicating the tension as the first force, we are also going to indicate the force of these 2m mass. That is the force of this 2m mass. That is the force of this particle A, which is actually 2mg sine 60 degrees, obviously representing the similar force on the particle B, which has mass 6m. We have 6mg sine 60 degrees. So also remember, we are also being told that this part of the plane is being rough. That is, this part of the plane is rough. Obviously we are therefore going to have the frictional force there, and the frictional force is given by mu times the normal reaction force which is being exerted on this particle B, which has mass 6m. That is, frictional force is mu times the normal reaction force, but the normal reaction force here is 6 mg cos 60 degree. I did not include it there, but actually, obviously, it's clearly, you can clearly see that normal reaction force is going to be 6 mg cos 60 degree, actually. So after indicating all the forces, we can therefore launch into the equation. That is, we are going to show that the acceleration of the particle is 3g divided by 8 times square root of 3 minus 1 meters per second squared. So the first thing we are going to do, we are simply going to apply Newton's second law of motion on both particles. That is, applying Newton's second law on particle A, that is particle of mass 2m, we are going to have what? First, in the first place, indicating first the acceleration of our system. That is, the acceleration of our system is pointing towards, that is, pointing the direction of the 6m mass. That is, the direction towards which a particle B is going to be moving. That is the acceleration. We are going to consider the acceleration being pointing in this direction. Now, so considering the acceleration being pointed in this direction, it means if you apply Newton's second law on particle 2m, we are going to have what? We are going to have t, that is, as I said, we are going to consider only this tension, that is t minus 2mg sine 60 to be equal to 2ma. Now, why are we even applying Newton's second law on both particles? So, most of the time when you see this type of question, the first thing you must do actually to apply Newton's second law on both masses, and you are going to obtain a set of equations. From that set of equations, you can obtain a lot of things by simply resolving those equations, actually. So if you apply Newton's second law on the both particles, we are going to see which relation we can have between the two for us to get the parameter which we are looking for, actually. So applying Newton's second law on particle 2m, we are going to get t minus 2mg sine 30 to be equal to 2ma. That is further simplifying, that is knowing that sine 30 degrees is half, we are going to get t minus 2mg times half to be equal to 2ma. And then this is therefore going to give us the expression t minus mg to be equal to 2ma. So let us call this our equation 1. Similarly, applying Newton's second law on particle 6m. So if we apply Newton's second law on particle 6m, considering the acceleration in this pointing in this direction, we are going to have 6mg sine 60, then minus t minus the frictional force, that is mu 6mg cos 60 to be equal to 6ma. So further simplifying, that is sine 60 is square root of 3 divided by 2 and cos 60 equal to a half. We are going to have 6mg times square root of 3 divided by 2 minus t minus mu 6mg times a half to be equal to 6ma. From which we get 3mg square root of 3 minus t minus mu 3mg to be equal to 6ma. Let us call this our equation 2. Now, since we have the two equations, that is equation 1, which we obtain by applying Newton's second law on particle 2m, and we have an equation 2 which we obtain by applying Newton's second law on particle 6m, we can therefore resolve these two equations to get our acceleration. That's it. We can clearly see that having these two equations for us to obtain the acceleration, but there's also another parameter, which is that there's also another unknown, which is the tension. So for us to properly resolve these two equations, for us to only get the acceleration, we can simply add the two equations. Why? Because adding the two equations, the tensions are going to cancel. The tension is going to cancel. So adding the two equations, we are going to get 3mg square root of 3 minus mg. Okay, that is 3mg square root of 3, then minus mg, then minus mu 3mg to be equal to what? To be equal to 8ma. From which, further simplifying, that is dividing all through by m, we are going to get 3g square root of 3 minus g minus mu 3g to be equal to 8a. From which we also know that is knowing that mu is given in the equation. That is, we know that the coefficient of friction between B and the plane is 2/3. We can therefore put it inside the expression. So put it inside this expression, we are going to get 3g, then times square root of 3 minus g minus 2/3, then times 3 to be equal to 8a. From which, further simplifying, we get 3g square root of 3 minus g minus 2d to be equal to 8a. And from which, further simplifying again, that is, we know that we have knowing that minus g minus 2d give us negative 3g. We therefore get the expression of the acceleration from here. That is, if we divide all through of the both of the equation by 8, we get the acceleration to be equal to 3g divided by 8, then times square root of 3 minus 1, okay, meters per second squared, actually. Now clearly I simply factor out 3g from here. That's factoring out 3g from here. We are going to get 3g factor square root of 3 minus 1. Then if I divide all through by 8, I get the acceleration. So getting the acceleration, and that's what we're being asked for us to get to prove in the A part of the question. That's the acceleration of the particle is 3g divided by 8 times square root of 3 minus 1 meters per second squared. So to actually learn to the B part, they're asking us to get the tension in the string. That you are asked to show that the tension in the string is mg divided by 4 then times 3 square root of 3 plus 1 Newton. So simply to do this, since we already have the value, since we already have the expression for the acceleration, we can therefore simply substitute the value of the acceleration either in equation 1 or equation 2. So we are going to substitute the value of the acceleration a into equation 1. So doing that, we are going to get t minus mg to be equal to 2m then times the acceleration which we have obtained. That is 2m times 3g divided by 8 times square root of 3 minus 1. From which, further simplifying, we get t to be equal to, that is sending mg on the right hand side, we are going to get it to be equal to 2m times 3g divided by 8 times square root of 3 minus 1 plus mg. From which, further simplifying, that is factoring out mg, because mg is common all through. That is factoring out mg, we are going to get t. Factoring out mg on the right hand side, we are going to get t to be equal to mg then times 3/4. Why 3/4? Because if you factor out mg from here we are going to be left with 6 divided by 8. So 2 can go into 6 3 times and 2 can go into 8 4 times. So we are going to get the tension to be equal to mg then times 3/4 square root of 3 minus 1 then plus 1, because we are going to be left with 1 since we factored out 3g from the right hand side expression. From which, at this level, further simplifying, we get t to be equal to mg. That is simply multiply 3/4 into this bracket. We're going to get t, the tension, to be equal to mg then times 3/4 then times square root of 3 minus 3/4 plus 1. Though doing the LCM here, we are going to get the tension to be equal to mv then times 3 square root of 3 then minus 3 plus 4 divided by 4. From which, further simplifying, that is, we know that negative 3 plus 4 give us 1. So further simplifying, we get t, that is the tension in the string, to be equal to mg divided by 4 then times 3 square root of 3 then plus 1 Newton, which is actually what was being required for us to prove in the B part of the question. Yes, so let us then actually launch into the C part of the question. The C part of the question are asking us to find, in terms of G and M, the force exerted by the string on the pulley. So that is, they're asking us to get actually this force M, which is the force exerted by the string on the pulley. Remember, this point here is at the top of the wedge, actually, okay? So when they're asking us to get the force exerted by the string on the pulley, we simply need to look at the place where we have the pulley, and from there, normally that force exerted on the string by the pulley, okay, simply separate the top of the wedge into 2 equal sides, and saying that, it implies we can therefore get the angle 45 degrees on both sides. Why? Because we know that we had 30 degrees on the part of the plane which was smooth and 60 degrees of the part of the plane which was rough. 60 plus 30 give us 90. Then for us to get the remaining angle, we simply need to make 180 minus 90 degrees, which give us 90 degrees. So we are simply going to separate those 90 degrees into 2. Why? Because the force exerted by the string on the pulley splits our top of the edge into 2 equal parts, which are symmetrical to each other. So we are going to get the angles 45 degree and 45 degree on both sides, actually. So we can therefore get that required force exerted by the string on the pulley. That required force is actually equal to 2d then cos 2t then cos 45, where t here is actually the tension which we have obtained in the B part of the equation. So substitute that is cos 45 degree, which we know, which is actually square root of 3 divided by 2. As well, we know that the tension T which we have obtained is equal to mg divided by 4 then times 3 square root of 3 plus 1 Newton, which we have obtained the B part. So substituting it into this expression of the force, we get F to be equal to 2 then times the tension then times square root of 3 divided by 2. From which, further simplifying, we get that the required force, that is the force exerted by the string on the pulley, to be equal to mg square root of 3 divided by 4 then times 3 square root of 3 plus 1. So how do we obtain it? Simply, we know that from here, if we multiply 2 here, we are going to get mg divided by 4 here. Then mg divided by 4, then if we mg divided by 4, then if we are going to have mg divided by 2. Why? Because if 2 enters here, we are going to get 2 mg divided by 4. So simplifying that is 2 is going to cancel the 4 down. 2 is going to go into 4 2 times. So we are going to be left with mg divided by 2, then times 3 square root of 3 plus 1. Then multiplying it times square root of 3. That is multiplying the expression being left inside, that is mg divided by 4 times 3 square root of 3 plus 1 times with square root of 3 divided by 2. We are going to get actually mg divided by 4 because we have a 2 here, then times square root of 2, then times this 3 square root of 3 plus 1, which is actually that required force exerted by the spring on the pulley. Let's then actually launch into the D part of the question. So in the D part of the question, we are being told that the D part of the question was being introduced with a small paragraph. That is, the particle B hits the ground 2 seconds after the system is released from rest. That is, the particle B hits the ground 2 seconds after the system is released from rest and does not rebound from the ground. That is, immediately the particle hits, that is, the particle B hits the ground 2 seconds after the system is released from rest and does not rebound from the ground. So in the question, they are asking us to show that the further distance, that the deeper the question, are asked to show that the further distance A travels before coming to momentary rest is actually G times the quasar times square root of 3 minus 1 all squared method. So this condition which we have here, that is the particle B hitting the ground 2 seconds after the system is released from rest, is going to help us a lot to get this proof actually. So how therefore can we proceed? We are simply going to use that we are first of all going to let that further distance move by A before coming to momentary rest to be S actually. So how therefore can we do, what therefore can we do to get this distance? So simply we are going to use Newton's equations of uniform acceleration. That we are going to use Newton's laws of motions actually. So we are simply going to obtain this expression from we're simply going to obtain the expression of S from here. Why? Because this X actually corresponds to that further distance which A travels before coming to momentary rest. Having all the conditions which we have, we are simply going to obtain the different values which we have, that is VU and A1. So to obtain VU and A1 here, we are simply going to use the conditions being given to us in the equation. So from this equation, that is from V squared equals U squared plus 2A1S, we can therefore get the expression for S. That is S is therefore going to be equal to V squared then minus U squared. This here included V squared, because it's actually this same V actually, and V squared minus U squared divided by 2A1 actually. So let us call it our equation 3 star, where V here is going to be equal to 0. Why? Because the system, that is, since A comes to momentary rest, was being told in the equation. That is, the equation will have to show the further distance A travels before coming to momentary rest. So the fact that A comes to momentary rest, it implies the final velocity of the particle A is actually going to be equal to 0 actually. So having this, it means we are simply going to be left to get the value of U and A1 respectively. So that is all we are going to be looking for in this particular question, because V is actually equal to 0. So we are going to be left with minus U squared divided by 2A1, and U which we are going to obtain obviously, and A1 we are also going to obtain it from the condition given to us here. So how therefore can we proceed to get the different values of U and A1? So note that immediately when B hits the ground, the system is moving with a speed V. So immediately when B hits the ground, the system is moving. That is, the particle A is moving with a speed V. And we can also use this expression for uniform acceleration, that is V equals U plus 80, to get that expression of the speed V of the system immediately when B hits the ground, where U actually is equal to 0 because the system was released from rest. So the system being released from rest, it implies the initial speed is going to be equal to 0. That is, U is actually going to be equal to 0. Obviously, we are being told that B hits the ground 2 seconds after the system is released from rest. So T here is actually going to be equal to 2. T here is actually equal to 2 seconds. And obviously, we also know the value. We also know the expression of A, which we have proved in the A part. That is A equals 3G divided by F, then times square root of 3 minus 1 meters per second squared. So having U to be equal to 0, having t to be equal to 2 and having the acceleration, we can therefore get that speed. That is the speed which the system is moving. That is the speed of a. Actually, that the speed the system is moving. That is the speed which the system is moving immediately when v hits the ground. So that speed v is actually going to be equal to at. Why? Because u equals 0 and a, we have a and t equals 2 seconds. So further simplifying, that is 2 multiplying 2 inside this bracket, we are going to get 3g divided by 4 then times square root of 3 minus 1 meters per second. So this value is going to be the value of u in our equation 3 star, as I said, actually. Okay, now you're therefore going to be left to determine the value of a1, because that is what's been left for us to find, because we already have u. We actually agree that v equals 0 since the system came to momentary rest. So you are simply left to get the value of a1. So the value of v which we have obtained obviously is going to be the value of u in the expression of s. Obviously, that is the initial speed of the system when v hits the ground. So we are going to be left to get the value of a1. So we also know that when v hits the ground, t equals 0, that the tension becomes 0. This condition will help us to obtain the value of a1. So from equation 1 which we have obtained, actually, that is from equation 1, that is when we apply Newton's second law on the particle A. Actually, we get this expression from equation 1, and from this expression we are simply going to get the value of a1. That is, this a here corresponds to a1, having in mind that the tension equals 0. So when t equals 0, obviously the acceleration a becomes a1, and equation 1 will therefore become 0 minus mg, because tension equals 0. So 0 minus mg to be equals to 2m then a1, from which we get the value of a1 easily. That is, to get the value of a1, we can simply divide all through by 2m, and from which we get the value of a1 to be equals to negative g then divided by 2. So obviously, having a1, having u, obviously we have v to be equals to 0, that is the final speed, to be equals to 0. We can therefore come into this our expression of s, that is s, which is actually that further distance which a travels before coming to momentary rest, is v squared divided by v squared minus u squared divided by 2a1, from which putting everything up, that is v, which we agreed 0, and u, which we have obtained here to be 3g divided by 4 then times square root of 3 minus 1 meters per second, and then a1, which is the acceleration, which is negative g divided by 2, from which further simplifying we get the s, that is the further distance a travels before coming to momentary rest, to be equals to negative 3g divided by 4 then times square root of 3 minus 1 all squared then divided by our negative g. The negatives are going to cancel on both sides. That is, clearly we get the required proof. Why? Because if you look it a little bit closer, this here, this negative with negative is going to cancel. We are going to count this negative and this negative is going to cancel. So at this level here we are going to have 3/4 then g. Now here we are going to have g squared, then divided by this g, we get g at the end. So this g, I can put it outside to get, therefore, that further distance which a travels before coming to momentary rest actually be equals to g times 3/4 times square root of 3 minus 1 and all square meter, which was actually what was being required for us to prove in the D-part. So thank you very much for watching this video, and don't forget to like, to subscribe, share for the others to benefit from the content. So thank you very much for watching the video, and see you then for a very next interesting video. Bye bye.